Okay, so actually the next two chapters have to do with bonding. It's such a broad topic and so critical to understanding the how chemistry actually works that the two chapters we're going to split into two separate exams. Okay, so let's proceed. The fundamental question behind all chemistry is, what is a chemical bond? What do we mean by a chemical bond? We can have simple definitions, we can have more complex definitions, but at least for our purposes, we need to have some concept of what a chemical bond is. And this slide is just questions. Right? We're going to answer the questions in subsequent slides. Then why do atoms bond with each other to form compounds? I mean, couldn't they just be happy enough on their own? Why do they need to bond? What is it that drives the bonding? And then if they are going to bond, what types of bonds are there? Because they're not all the same. We know that from general experience up to this point. And from discussing concepts of well, just simply naming compounds, we have to consider whether the compound is ionic in nature or is covalent in nature. Right, so we're going to address that topic also. And to understand the bond, there's no way to get at it with laws only. Laws just will not say what we need to know about the bond. We need a theory. We need a model. And the first one of those that was proposed was by John Dalton in England in early part of the 19th century. And this laid the foundation for understanding chemical reactions, his atomic theory, and eventually led to an understanding of the chemical bond. As luck would have it, there's really no simple or complete way to define it. Some theories help us understand the chemical bond when in terms of certain types of reactions. And then other theories help us understand it in other ways. There hasn't been a complete, well, there has been a complete synthesis of information to define what the chemical bond is. But that theory is beyond most general chemistry students and instructors for that matter. So some of the simpler concepts actually answer the questions that we need to, that are asked without getting so complex or so heavy, for lack of a better term, into the more advanced theories. So, in general, the chemical bond is an expression for a force that holds atoms together and makes them function as a unit. Right, so let me say that again. The chemical bond is a force that holds atoms together and makes them function as a unit. And when they do that, that gives them different properties. The elements that formed this bond, let's keep it simple. For instance, if we say an element we have a metal and a non-metal, right? We know in general that metals have certain characteristics, non-metals have certain other characteristics. When they come together, you have a completely different substance. So that's how we explain. See, I got something popped up on my screen here that's getting in the way, and it won't go away. I'm sure you can't see it, but it's annoying. Hold on a second. There it goes. It's gone. Okay. So in its simplest form, it's just that force that holds atoms together. One thing we do know, now this is a generality. It doesn't always hold. A bond will form if the energy of the aggregate, that is, whatever the combination is lower than that of the separated atoms. In other words, if we look at energy on this scale and the distance between two atoms on this scale, so they're farther apart if they're out here, closer together if they're here. And this is the total energy of the system that they're in. If they're this far apart, then they might have this much energy. And as they get closer, that's starting to form a bond. And they'll get down here and they'll reach a minimum. And then they'll go back up like that. So this is where the bond forms. And that holds in most cases. So why does it go up so high this way? Well, if you actually force the atoms closer together, then they start to feel each other's positive nucleus. And then all bets are off. So this is the minimum, that's where the bond forms. When the energy is at a minimum. It's more stable there. Minimum energy means stability. All right. So we're actually going to start off talking about bonding in terms of complete ions. So now we're talking about what we would call an ionic bond, where the electrons are transferred from one atom, from the sodium to the chlorine. So now we have the chloride ion and the sodium ion. And the attraction now is purely electrostatic. And it can be calculated. All we need is Coulomb's law. Right? And here's Coulomb's law. The energy equals, and the energy of the system is equal to the charge of one times the charge of the other, divided by the distance between them, and times this proportionality constant. Right? So that gives us the energy of the system. And if you introduce those values for this system, sodium and chlorine, you get this value. So that is a representation of the bond energy. And notice, since the bond energy went negative, that means they're more stable, right? The energy had to leave the system, so the energy of the system went down. If the energy were positive, you can expect that you would not get a bond. And that would be obvious in this case because both of these would have to be positive, or both of them would have to be negative, and then they'd repel one another. And you definitely wouldn't have a bond then. Okay. All right, so in the case where you don't have charges, right, say two hydrogen atoms. Remember, hydrogen is one of those diatomic elements. In nature, under what we've considered normal room temperature and atmospheric pressure, hydrogen exists as that. And it's not the only one, right? Nitrogen does it. Oxygen does it. Fluorine, chlorine, bromine, iodine, they're all diatomic. And since they're the same atom on both sides, it can't be ionic. There's no way, because they're attracting electrons equally. Right? So now we're talking about a covalent bond where they have to share electrons to form the bond. So there's a balance between attraction and repulsion. Right? You get an attraction on some level between the proton of one and the electrons of the other, and vice versa. But that attraction only goes so far until you get repulsion. So it's sort of a balancing act. They get just close enough to where the energy is minimized. Again, whether it's covalent bonding or ionic bonding, the concept still holds. Minimum energy is the desirable position. Oh, they actually drew the graph for me. I didn't notice before. Okay, so as the hydrogens get closer together, the energy tends to drop until you start trying to push them too close together. And then they begin to repel one another. So they're most stable here at this distance, 0.074 nanometers, I believe. Yeah, here it is, nanometers. Okay. Okay, so just to summarize, the key idea for bonding is if the electrons are completely transferred from one to the other, then you get electrostatic attraction, and that's ionic bonding. But if there's not a complete transfer of electrons, particularly if they're both identical atoms, then you get covalent bonding. But if you try to form a covalent bond between two atoms where one of them attracts the electrons a little bit stronger, but not enough to completely steal them from the other, then you can get some polarity difference, some charge distribution difference between the atoms, and you get a covalent bond, but it could be polar in nature. Those are the intermediate cases. Let's see, let me keep up with my hard copy here. Okay, so you can form a continuum, so to speak, between completely ionic and completely nonpolar covalent. And somewhere in between, you'll find the bond that you're interested in characterizing. Nonpolar covalent bonds. Virtual equal sharing, and that's why I put equal in parentheses, I mean in quotes, because there's equal and then there's equal, right? There's genuinely equal where both atoms are identical, and that would be the ideal nonpolar covalent bond. But there's some where the attraction is so similar between the two that the charge distribution is not very shifted very far. So there's virtually no charge separation in the bond itself. Now, if you get a significant shift in electron density to where it spends more time around one than the other, an example would be HF. hydrogen fluoride. Fluoride is the strongest attractor for electrons in the periodic table. And I think we covered that, didn't we? The concept of electronegativity. I have to teach too many courses. Yeah, periodicity. Okay, yeah, we just covered that. Okay, so I can use those terms. So the electronegativity of fluorine is the highest in the periodic table at 4. Hydrogen is somewhat less than that. It's probably around 2 or 2.5. So there's a huge difference between the two, but it's not enough to form an ionic bond. So you get an unequal distribution of charge. That's what that little delta means. It's not a complete transfer. It's just a slight difference. So you have more electron density over here than there, and that gives you a polar bond, which we designate with an arrow like that. This shows the positive end. This is pointed toward the negative end. And when you see that, that's also known as a dipole moment for the bond. So it forms a dipole. In other words, it's got 2 poles, a positive and a negative pole. When that happens, you have a polar covalent bond. Okay, and that can be measured. Right? You can put hydrogen fluoride in between 2 electrical plates. One's negative, one's positive, and the way that these molecules affect the charge between the plates can be measured. And that interpretation tells you the actual measure of the polarity of the bond in that electric field. Okay. So what do we mean by a chemical bond? It describes the forces that hold atoms together to form a functional unit. Why do atoms bond with each other? Generally speaking, it's to obtain minimum energy. So as separate atoms, they have a certain amount of energy. If they combine together, then their total energy is reduced, and they're consequently more stable. And atoms bond with each other in one of 2 ways, generally speaking, either ionic or covalent. Okay. I thought we covered electronegativity already. When we talked about periodicity. And well, it won't hurt to talk about it again. The concept of electronegativity, or the strength with which an element attracts electrons to itself, was first proposed by Berzelius in the first part of the 19th century. And it's been studied by others ever since. And there have been attempts to quantitatively describe that attraction of electrons. And there are several systems out there. The one that's most commonly used is Linus Pauling's system. That's the one that gives us a value of 4 for fluorine, and everything below and to the left is a smaller number, on down to less than 1 when you get to cesium. Now there's a formula that goes with it. I mean, Linus Pauling didn't just pull that out of thin air. It's actually based upon measured values. And in fact, that's not the only thing that Pauling deserves credit for. In 1954, he received the Nobel Prize in Chemistry for his research on the nature of the chemical bond. He not only did research on the bond, he actually published a book that synthesized everything that we knew up to that point into a coherent story or a theory for the nature of the chemical bond. And that book, in addition to his other research, was what won him the Nobel Prize. He also, actually, he's the only scientist who's received 2 Nobel Prizes in 2 different areas. There have been others that received 2 prizes in the same area, but he got one Peace Prize for his activities on nuclear non-proliferation. I'd prefer to laud his work in chemistry rather than nuclear non-proliferation. That's a sore spot for me, and I won't talk about it right now. Anyway, so this is a general discussion of Pauling's method of determining electronegativity. And you don't have to memorize this formula. It just illustrates how he arrived at his numbers. So if he has a molecule that's bound between hydrogen and that other atom, we compare by measuring the bond energy of HX and then the expected bond energy that can be calculated based upon the separate bond energies of the where H is bound to its neighbor, its lookalike, and X is bound to its lookalike. And then you take those 2 energies and divide by 2, and that is the expected bond energy for HX. And that's used to determine the electronegativity for this doesn't give you the value of electronegativity. This is one step toward that. Right? So these relative values where fluorine is 4 and everything else is less are relative to one another. And that becomes important when you try to quantify whether a bond is polar or nonpolar. So the way you do that is, okay, so I'm sorry, we're still talking about electronegativity. So this difference where you have the actual value for that and the expected value for that, right? We determine the expected value over here, and then you have an actual value for that bond energy, and that can be determined through experiment. Then the difference between the two gives you a measure of electronegativity. If H and X are identical, then of course delta is going to be 0. That's an easy one. If X has a greater electronegativity than H, then the electrons will tend to be closer to X, and the charge distribution will be as described earlier. Maybe we didn't talk about electronegativities. Am I even in the right chapter? Yeah, okay. Okay, so electronegativities increase from lower left to upper right. And as reported, and this will be in your textbook also, as reported from lower left cesium up to fluorine, the electronegativities generally increase. So the increase going up and the increase going to the right. Now, why is that? I think we already talked about that, didn't we? Yeah, I know we talked about that in the last chapter. Why that is. Now we're going to use that information to determine the polarity of a bond. Okay, so they range from 4 in fluorine and 0.7 down at cesium or francium. They're both the same values. Here we go. Now notice, if you across the transitions, you tend to get the same trend up until you get to the end, and then it goes back down. It starts at the level in the neighborhood of the middle of the period of the transition metals. So it's not foolproof as far as trends go, but it is foolproof as far as actual values calculated. So you can use these values. There's hydrogen 2.1. So 2.1, what you do is you subtract the lesser value from the greater value, and that gives you a number. And then you compare that to what we know about the behavior of molecules with those single bonds. Okay. So which one of these would have the greatest attraction, lithium or fluorine? Lithium's on the far left, fluorine's on the far right. So fluorine would have the strongest attraction for electrons. How about fluorine and iodine? They're in the same group. So the trend would be fluorine at the top would have a stronger attraction. Let's see, we've got another attendee here. Okay, so that's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the stronger attraction would be for fluorine. Okay. This is just a restatement. Okay, I guess it was important enough to put it in the slide, so we'll talk about it. As we go across the period, the reason the electronegativity increases is because we're increasing the effective nuclear charge, more protons. But we're adding electrons, but the increase in number of protons is increasing the strength of electrical attraction. So why does it increase when we go up in a group? Well, remember the size of the atoms. They're bigger toward the bottom than they are toward the top, smaller. So you get, and the bigger atoms have more electrons on the inside. Right? So any electrons coming from the outside are not going to feel the full force of those added protons on the inside, because we've added so many electrons that tend to shield them. So the effective nuclear charge of elements as we go down in a group actually decreases because of that shielding effect. So as you move up and the number of electrons shielding the protons decreases, as you move up the energy levels and you get really small, like lithium, for instance, is small compared to cesium in its own family. Then you get what's known, you invoke an expression called charge density. The charge density of the nucleus actually increases as we go up. And that draws electrons more strongly. That increases the electronegativity of the element. Okay, so how do we define the nature of the bond if we know the electronegativities of the individual atoms? You subtract them. Like I said before, you subtract them and you look at the values. If the value is very large, then at some point you can call it ionic. And in general, we say if the difference in electronegativity between the two atoms is greater than or equal to 1.5, that bond is ionic. If it is anything less than 1.5, we say it's covalent. And then we say, well, is it nonpolar or polar? The breaking line there is 0.2. If the difference between the electronegativities is greater than 0.2, but less than 1.5, then we have a polar covalent bond. And anything less than 0.2 is nonpolar covalent. All right? Now, it's important to understand also that even though we classify them in terms of whether they're nonpolar covalent, polar covalent, or ionic, every bond has an ionic character and a covalent character. It's the balance between the two that determines overall polarity, whether it's nonpolar, polar, or ionic. So let's see if we can use what we've learned here to order these. Well, in this case, we're just looking for most, oh yeah, we are, order from most to least polar. So the most polar would have the largest, if we had the values, would be the largest difference in electronegativities. But we don't have that, so we're going to have to use trends in the periodic table. So the first one is easy because the X element is fluorine in each case. So we just need to look at how far away are they from fluorine. Right? Well, we look at nitrogen and fluorine. That's nitrogen is 2 to the left, oxygen is 1 to the left. So we have fluorine here, then we have oxygen, then we have nitrogen in the periodic table arrangement. And then carbon, always even further, right? So if we're going from most to least polar, the most polar will be these two. The next would be these two. And the last would be these. Sorry, I gotta stop eating popcorn before class. Okay, so carbon, nitrogen, oxygen in that order, from most to least polar. How about the next one? The next one is a little more difficult. So carbon and fluorine are like that. Nitrogen and oxygen are here. Silicon, where is silicon? Silicon is in carbon's family. So silicon is down here. Right? So we have the most polar should be, actually, well, it's kind of a toss-up, isn't it? Between carbon and silicon. Silicon has more metallic character is the way I would break that tie. So I would say silicon would be more polar than, what's our other one? This one. Or more polar than these two that are very close together. Like that. Now see if I'm right. Or if the slide agrees with me. Yeah. Oops. About to give away the answer for the third one. All right, for the third one, we've got 2 chlorines, right? Chlorine's down here. So 2 chlorines would be the least polar. It'd have to be. I mean, it's 2 of the same atoms. So we can put that one right there. Boron and chlorine. All right, so boron is up here, that one and that one. And then sulfur and chlorine. Where's sulfur? Sulfur is here. Right. So this would be the next one. They're right next to each other. And then this one would be. That would be the most polar. Now we're just talking about the bonds. It doesn't matter if these are actual compounds or not. All right. So which of these would be the least polar and still be considered polar covalent? So this is a situation where you need to read the question carefully and actually work your way backwards. So first of all, they have to be covalent, right? Are there any in here that are not covalent? Magnesium and oxygen are not covalent, right? So that lets that one out. Are there any others? Silicon, oxygen. Let's see. What's the difference between silicon and oxygen? 3.5 minus 1.8. 1.7. That's ionic, right? Based on our list, right? Greater than 1.5. So silicon and oxygen are also, I didn't have to do magnesium, oxygen. I know they're so far apart, they have to be ionic. But silicon and oxygen, we confirm, is also ionic. So it can't fit. It's not covalent. So the others, it looks like the rest of them are nitrogen, oxygen, oxygen, carbon, oxygen are covalent. All right. Now we look at the polarity. Which one is nonpolar? Oxygen, oxygen. Right? It's perfectly nonpolar. It can't be polar covalent. So now all we have to do is decide between carbon, oxygen, and nitrogen, oxygen. Which would be the least polar? You look at the separation. You can do the calculation, fine. Carbon, oxygen here between the two is 1. Difference of 1. Nitrogen, oxygen is a difference of 1/2. It would be the least polar, yet still polar covalent. Let's see if that's true. Let's go back. Right? Polar covalent, it's got to be 0.3 to 1.2. So both of these would be considered polar covalent, and nitrogen, oxygen would be the least. Okay, so that's our detective story. All right. Most polar without being considered ionic. Well, obviously. Well, wait a minute. Most polar without being considered ionic. That's not right. We just said silicon oxygen was ionic, didn't we? The difference between silicon and oxygen is 1.7. Right? 1.7. That's ionic. Okay, so there's an error in that slide. I got to fix that. Here we go. So if silicon and oxygen can't be it, then instead of silicon oxygen, it needs to be most polar without being considered ionic. That's still nitrogen oxygen, isn't it? No, the most polar, excuse me. Carbon oxygen. Right. There's carbon, there's oxygen. The most polar without being considered ionic. So I need to fix that one. It's actually carbon oxygen, not silicon oxygen. Okay. So I mentioned this earlier, the dipole moment. The dipole moment, I think, can be considered for bonds, but it's also more commonly used to describe whole molecules. So if you have a molecule with 2 or more bonds in it, you've got to consider all of the bonds and how they affect one another to determine the overall dipole moment of the molecule. Right, and this is the arrow that we use. Of course, the arrowhead is pointing toward the negative side, this positive obviously toward the positive side. Two factors always determine the dipole moment or the polarity of a molecule. First one, does it have polar bonds? What is the polarity of the bonds that make up the molecule? The individual bond polarities. Then once you know those, how are they oriented in space? How do they affect one another? The geometry of the molecule. For instance, if we have this one, that would be carbon dioxide. The individual bonds are polar in this direction. Okay? But they're pointing in opposite directions. So when you add them together, taking into account that they're pulling in opposite directions, you get an overall dipole of 0. Carbon dioxide is a non-polar molecule, has no dipole moment simply because of that fact. Water is another subject. Water is a bent molecule. Each of the bonds has a dipole that direction, and when you add them together, because they're not pointing toward each other, when you add them together, you get an overall dipole like that. Right? That's why water boils at 100 degrees Celsius rather than at minus 50 or 60 degrees Celsius, if it were linear. And that's good for us, because if it were not 100 degrees Celsius, then there would be no liquid water on the surface of the earth. And any water that we had would immediately vaporize. Of course, that would be fatal. And there's carbon dioxide. That's not a very good representation because it's only got one bond here. It needs two. Okay. So what this is referring to, this addition of these dipoles, is called vector addition. A vector is an expression of magnitude and direction. So if I say, I'm in my car and I'm driving 50 miles an hour, I would be 50 miles an hour on a straight road or a curved road. Doesn't matter. I didn't tell you that information. But if I tell you my velocity is 50 miles an hour, then it would be 50 miles an hour this direction, but it may only be, well, it would be 50 miles an hour at this point. But I would change direction over here, and it might be 50 miles an hour that direction. What? Oh. All right. This is a vector because I'm telling you the direction. Well, dipole moments are considered the same way. This is a vector of that magnitude, but this one is the same magnitude in opposite direction. And when you add vectors together, you have to take their direction into account at the same time. which means these cancel one another out. These are pointing equal magnitudes in 3 equidistant directions. So they all cancel one another out. This one is a tetrahedron, and they're pointing in equidistant positions. They cancel each other out. So all of these molecules are nonpolar. Even though their bonds are polar, they're all nonpolar because the vector addition of each of their dipoles cancels. All right. Here's one of the driving forces for why this is an early explanation for chemical reactions. And it can be summed up in the Octet Rule. Atoms, in general, and many of them, this is true, they tend to acquire a noble gas electron configuration when they react. Okay, let me say that again. Each element, when it reacts, tries to look like a noble gas. And that means it has an octet in its valence shell. Okay? So for instance, if we were talking about a reaction of oxygen with some other element, what would make it look like a neon? You need to add 2 electrons, correct? And we've done the electronic configuration for oxygen. Yeah, 8. So it's 1s2, 2s2, 2p, 4. So where are the valence electrons? Those are the valence electrons. There are 6 of them. So what would make it look like neon? Add 2 more. Now it has this configuration. It has the octet. Now this rule only works for S and P together. When you start getting D involved, then it doesn't work so well. So that's why it's one of those theories where we don't want to throw it away because it works some of the times. So we restrict its application. Okay, so this would look like neon. But if we put 2 electrons up here, what does that mean here? That means it's acquired 2 more electrons. Now, how does it do that? Well, it can do it in one of 2 different ways. It can do it by forming ionic bonds or covalent bonds. If it forms an ionic bond, then where did it get those 2 electrons? Well, let's say perhaps it got those electrons from sodium. Right? Sodium has 11, so it's going to be 1s2, 2s2. 2p6, 3s1. So sodium wants to look like neon too, but it's easier to remove an electron and look like neon than it is to add 7 electrons and look like argon. So it loses this electron. That makes it a positive charge. And if it gave that electron up here, there would have to be 2 of them, wouldn't it? 2 of those. to give 2 electrons. So that's why sodium oxide is written that way. And by losing that one, now we're back down to this octet. Right? It works best for period 2 and period 3. Notice period 2, there are no p orbitals. I mean, there are no d orbitals there. Period 3 is getting a little sketchier because even though we're passing across from this p s to this p, the d orbitals are there. Right? Remember, when n equals 3, you can have d orbitals. 0, 1, 2. 2 is d. 0 is s. 1 is p. 3 is 2 is d. But they don't come into play because we're moving here. There are not enough protons to warrant the addition of that many into the d orbital. So we're really only filling the 3p. Okay. Exceptions to the rule. So this would honor the octet rule. But if you tried to form a compound with, say, arsenic and, say, arsenic oxygen, arsenic oxide, then it's possible that you're actually, for arsenic, you may exceed the octet. Now, I don't know that true. That's just a possibility. And that happens with periods 4 and above, simply because they now have access to d orbitals in spades. And the d's, right, they can have 10 electrons. So you've got all that room for those extra bonds to form. So the octet rule is really most valuable for period 2 and 3. Okay, here's an example, point in case, a case in point. 10 could have a 2+ or a 4+ charge if it's going to form an ionic bond. Lead can also be 2 and 4, right? Where are they located on the periodic table? Tin and lead. Let's see, here we go. Tin's right here, lead's right there. Okay. So if you lose 2 electrons from tin, you're over here now with a full d orbital. Doesn't say anything about that one. Right? So you're not really anywhere near noble gas configuration. If you lose 4, where does it come from? Well, actually, if you lose 2 from here, it comes from the p orbital. If you lose the other 2 to make it 4+, it comes from the s orbital. Because this is 5, that's 5. This is only 4. So you leave the d's intact and you take the electrons from the p's and the s's. Now, if you do that, then you end up with krypton as your electronic configuration. Okay. All right, other examples. All right, those were examples of ionic compounds. When 2 nonmetals react to form a covalent bond, they can still tend toward octets, but they're not mathematically octets. They're more perception of the individual atoms. So let's say we have, let's make it even simpler. Not just octet, but duet, right? Hydrogen would like to acquire an electron. If it has 2 electrons in its shell, it looks like helium. So how would we do that? Well, hydrogen has 1 proton and it has 1 electron. Right? Represented with a dot. It's only got 1 electron. Here's another hydrogen. It's got an electron. So if they come together and form a bond, it can't be ionic. We know that. But hydrogen thinks it looks like helium when you do this. Now hydrogen thinks, oh boy, I got 2 electrons now. But this other hydrogen says, oh boy, I think I've got 2 electrons too. We didn't add any electrons to give them each 2 uniquely of their own, but the covalent bond makes them think they have 2 electrons. That one thinks it, right, in quotes, thinks it has 2. This one thinks it has 2. So it makes a duet. You can do that for the octet with other elements like, I don't know, oxygen, nitrogen, fluorine, chlorine, bromine, iodine. The sharing gives them the feeling as if they have an octet. See, this thing's probably walking on me. No, it's better than I thought it would be. There we go. Okay, how am I doing on time? 3 o'clock. All right, I got about less than 40 minutes. And let's see. I want to get to a certain point before we stop, so I better get a move on. There's a convenient breaking point here in the middle. Okay. Remember what a representative group element is. Filling the s orbitals and the p orbitals. In other words, over here and over there. Not including the transition metals. Those are representative groups. Oops, sorry. Each of these elements has the same number of electrons, right? And they all look like neon. That's why they have the charges that they do when they form ionic compounds, right? Magnesium is an alkaline earth. It's in the second group. It has a 2+ charge. That was the way we learned it to begin with. This is why it is, because it looks like neon. Fluorine, add an electron. It looks like neon. These are isoelectronic series. They all have the same electronic structure. Okay, we're gonna have to skip this one. Just because we're running out of time. We learned in the chapter on periodicity that the periodic table allows us to predict many properties of elements. Atomic size, radius, ionization energy, left out electron affinity, and electronegativity. If we know the structure of the periodic table, we can easily write the electronic configuration. It helps us to predict formulas for ionic compounds. And it also helps us to determine if the bonds are polar or not, if we're dealing with covalent compounds. Okay. What are the factors that influence the stability and the structure of solid binary ionic compounds? Okay, so now we're narrowing our focus onto binary ionic compounds. For instance, sodium chloride or potassium chloride or, I don't know, lithium fluoride. Those are definitely ionic, and they form solids with a crystal structure, right? I've shown you this representation before where you have sodium and it's surrounded by chlorines. It's got chlorines in front and back, so there's 6 of them here. But each of those chlorines is surrounded by sodiums. Right, so this forms a crystal lattice. And when we write NaCl as the formula, that's the simplest whole number ratio for that crystal lattice. Well, there's an energy associated with that. What is the energy holding that thing together? And we express that in joules per mole of ions, or actually joules per mole of the formula. That lattice energy can be calculated, but we have to be specific about what the lattice energy actually represents. So we start with separated gaseous ions. In this case, we would have sodium ions as a gas. And we would have chloride ions as a gas. Oops. And when they come together, they form the solid, sodium chloride solid. That's the reaction equation that's associated with the lattice energy. So when you get these separate ions come together, what do you think? Endothermic or exothermic? It's definitely exothermic. These are far apart. They have their own high energies. When they come together in this lattice structure, they give off energy. So the delta H is going to be negative. In fact, large negative. Now, this can also be calculated from Coulomb's law. So this is how you would measure it. You would measure the release of energy when this happens. And then the calculated version would be in terms of Coulomb's law, where you have this proportionality constant, and it's, I don't know what it is right now, but it may be specific for this particular reaction. You have the charge here, the charge there, like 1 and -1, then the distance between them in the crystal lattice. Shortest distance would give you a calculated value for the lattice energy. So when you actually form a solid, right? Remember the formation, energy of formation, the standard energy of formation for a compound, you start with this one as 1 molar, right there. And then the elements are what are the natural states of elements at standard temperature and pressure. So in this case, it would be chlorine gas. In this case, it would be sodium metal. Right? So when you actually form that compound from its elements, and this would have a delta H of formation, which is not the same as the lattice energy. Right? It's different. Then you need to go through separate stages. For the metal, you got to turn it into a gas. That takes energy. It's endothermic. Then you take that gaseous metal and you ionize it. Right? You kick off an electron or more, depending on what charge you need. That's endothermic. Then for the nonmetal, you may have to dissociate it. In this case, you break the chlorine apart into separate chlorine atoms. Starts as a gas, ends as a gas with separate atoms. Next, you take those and ionize them. So this is also exothermic. Let's see, this is endothermic, requires energy, but this is exothermic, right? So as the electron attaches itself, electron affinity, remember, attaches itself to the X gas, or the chlorine gas, individual atoms, it gives off energy. And now that you've got the ions here and here from that process, they come together and form the solid. The lattice energy is this last step, 5. The overall for everything is formation, heats of formation. This is what it would look like on a graph, and this, I extracted this straight from your textbook. So we're not going to spend a lot of time on this one. Just to point out things like that I mentioned earlier, this electron affinity, right, for that ionization, ionization energy for the metal, electron affinity for the non-metal, other things that happen here. Oh, these are 2 different processes, right? This one on this side is for sodium fluoride. The one on the left side is for magnesium oxide. Okay. Let's see. This is taking, actually, this is taking a sample, a representation, a real world process for a lithium fluoride. Right? This would be the energy of formation, delta H sub F. And these are the processes that would go through with the values that are associated with it, right? So if we go step by step by step, each one together, add them all together, then the difference is this overall change is minus 617 kilojoules per mole. And notice if we go back to the original, here, it's per mole of solid formed. So that's the formation, energy of formation that we calculated by doing each of those individual steps and then adding them together. Here it is again, right, in a table. And there are several problems in the work problems document, in the review document. The work problems is a companion to that. That give you practice doing these. And we'll run through hopefully one of them when we look at the not Wednesday, but the following Monday, we'll do a review. And during that time, we'll look at least one of these. Okay. So I mentioned earlier that every bond has a certain ionic character. And as a matter of fact, no bond is 100% ionic. Now, why would that be? Well, every atom attracts electrons because of its protons, right? So in order to have a purely 100% ionic character, you would have to have nothing but positives on one side and nothing but negatives on the other side, so that they could be purely Coulombic attraction. But since these ions still have some negatives in there, along with the positives, you never get 100% ionic character. The way to calculate the percent ionic character is you have a calculated dipole that we did earlier, and then the measured dipole, and you just ratio them times 100. And here they are on a scatter plot. Percent ionic character on this axis, right? And electronegativity difference on this axis. So the greatest electronegativity difference, it looks like, is should be cesium fluoride, right? cesium fluoride. But it has less ionic character than you would expect. Lithium fluoride has a greater character, ionic character. Why is that? Basically because the cesium ion, while it's a single positive charge, and lithium is a single positive charge, lithium is a much smaller ion. The charge density is much higher, and the ion is smaller, so it can get closer to the fluoride ion. So there you have the Coulombic law in effect. The distance between them is shorter, so the strength of attraction is much higher. So electronegativity difference doesn't tell the whole story. Okay, so I had a professor when I was working on my PhD. He was advising me on some things. And I was developing a procedure to analyze soils for a certain mix of different types of elements. And he told me, that there's no theoretical basis for this. Your procedure is operationally defined, and let it go at that. And apparently everybody in my committee was happy with that, so I wasn't going to argue. This is an operational definition of an ionic compound. Right? We just say, if the compound conducts electricity when it's melted, it's ionic. So why would we have to melt it? Well, think about it. If you have a crystal of sodium chloride, right, and I've looked at them with magnifying glass on the bench top when I spill some salt, they're in little cubes. They're crystals. So what are the ions doing? They're locked in the crystal structure. They can't move. In order to conduct electricity, you need mobile charges. Right? Neither the sodium nor the chloride can move. So a solid crystal of sodium chloride is an insulator, electrical insulator. When you melt it, now those ions are free to move past one another. It will conduct electricity. By the same token, if you put sodium chloride in water, it will also conduct electricity because now the ions are mobile. Water, pure water, is an electrical insulator. It doesn't have enough ions to conduct electricity. Except when you increase the voltage so high, it electrolyzes the water, splits the molecule apart into separate ions. Then you can conduct electricity. So that's why you don't want to take a bath in a lightning storm, because water can become conductive if the voltage is high enough. Okay, so we need models. Let's see, hold on a second. Where am I with respect to all these? Okay, so I've got a few more slides. Maybe I can get them done. What is a model? Simply put, a model is an attempt to explain how nature operates. We can't see how it operates on the microscopic level, and that's what chemists are interested in. We can't see how it operates on the microscopic level. So we build a macroscopic model of the macroscopic world, as it were, to describe what's happening in the microscopic level. So you might have a molecular model set where you have atoms and sticks that form the bonds, and you put them together and you visualize how the molecule is arranged. That's a macroscopic model of the microscopic world. But it's important to understand that the model is not reality. It's a representation. It's a visual aid in that case, Sometimes the models are mathematical. In that case, they're mathematical aids for understanding the microscopic world. So these are the fundamental properties of models. First one I've already given you. You have to recognize the model is not reality. That's very important. Number one rule. Models are in fact oversimplifications. In other words, we try to incorporate the major factors into our model. Those things that have significant impact on the results of manipulations. Minor components are left aside until maybe later, then you'll incorporate those. But the model in its inception is oversimplified. And they tend actually to become more complicated over time. Why? Because of those three choices that we have, right? For a theory, this is our model choices. What happens when the model fails? When it does not adequately describe reality? You can throw it out. Start over. Or you can restrict its use. Say, it's only good under these circumstances. And many models are still used that way. Or you can modify it. And that tends to be the first choice. Nobody wants to give up on their model. It's kind of like a child. So if you propose a model in a research paper and they find out later that it fails, say, okay, I'll modify it. I'll make some tweaks to it so it'll satisfy. That's why it becomes more complicated over time. And most models become so complicated, you either restrict their use before somebody throws them out. Because if the scientific community decides that your model is worthless, then you don't have to throw it out. They'll throw it out for you. You also must understand the underlying assumptions in a model so that it is not misused. In other words, you can't apply it where it was not intended to be applied. Kind of like weather forecasting, weather models that are used, that are modified and used to predict global warming. In fact, none of the models that are used to predict an increase in temperature work. They do not predict accurately changes in temperature. That's a fact. All of them fail. That's because they're using them where they weren't intended. So if these predictions are proposed to be factual and that we need to change our economies and actually destroy our way of life just to satisfy the elite group that says that our planet is warming and we're causing it, so we got to do something about it. Those people have used models incorrectly. And the models that they use have actually been built-in fudge factors to give them the answers that they want. That's my soapbox on that topic. Now, before you throw out the model, if the model is wrong, you can learn something about reality, about the real system, by saying, all right, where did it miss? Why was it wrong? That can inform you of some basic nature of the real system. So don't just throw it out without investigating first. Okay, so here it is. This is what you do when your model doesn't work anymore. Now, this example of Newton is not chemistry, but it's a good example. Newton's laws of motion, known as classical physics, they only work in the middle size, right? On the order of large planets down to small, actually atoms. Newton's laws still work. If you get any smaller, like get subatomic or even less, or you get really huge, like black holes, Newton's laws completely fall apart. So we don't use them there. For black holes, we use relativity, Einstein's business. For very, very, very small things, we use quantum mechanics. And that's where chemists operate, in the quantum mechanical world. And we'll talk about that a little later, next time we meet. So I'm about to run out of time here. Modifying models. Here's from the sublime to the ridiculous. Physicists are so grasping for explaining the natural world that some of them have created a mathematical models with 26 dimensions, not just length, width, depth, and time. They've got all these other dimensions that you can't possibly visualize except in a mathematical model. Or throw the model out and start over. For instance, J.J. Thomson's plum pudding model of the atom. Right? Rutherford proved that one to be absolutely wrong. There was nothing to do. I mean, you couldn't go any further with a plum pudding model. It had to be discarded. All right. So let's see. I've got a few more minutes. When we talk about bond energies, actually, what do we mean? Well, go back to our original definition. If the chemical bond is a force holding two atoms together, then what would it take to break the bond? You have to add energy, right? Add energy to it to break the bond. So that also says if the bond forms, you get energy out. So breaking bonds is an endothermic process. Put energy in. Formation of bond is an exothermic process. Energy is released. With the same sign conventions that we used in thermochemistry. Energy into the system is positive. Energy leaving the system is negative. Okay, what types of bonds are there? Well, the only three I know of are single, double, and triple bonds. And the bond always represents a pair of electrons. Now we're talking about covalent bonds. We're not talking about ionic bonds anymore. Covalent bonds, for instance, a single bond would be hydrogen, hydrogen. That is 2 electrons. Oxygen would be a double bond. That's 4 electrons. Nitrogen is a triple bond. So that would be 6 electrons in those bonds. 1 pair each. What we've noticed also is that the length of the bond decreases with the more bonds you have. The distance between them would be here. The distance between oxygen would be there. The distance between nitrogen would be there. So the more bonds you have, the shorter. It's important, though, to recognize that the difference in distance is not a linear, right? So just because we have 3 bonds doesn't mean that it's a third the distance. It's actually more than a third. You do get closer, but you don't get linear closer. Okay, here we go with bond energies, right? So these bond energies, and they don't have a sign. Generally speaking, when we say bond energy is how much energy comes out when the bond forms. So that's why they're all without negative signs, they're positives. These are exothermics. So the bond energy is in terms of the hydrogens coming together in this first case, forming a bond, releasing energy. in the form of 432. Actually, there's, left the units out. I think it's kilojoules per mole. And you notice that for this family, HF, HCl, HBr, HI, the bond energy for HF is very high. And it gets less as you go down, and the ion, not the ion, but the atom gets bigger. It's pushed further away from the hydrogen. Further away means lower energy bond. If you're in a homologous series like this, HF, HCl, HBr, HI. And then we can look at, over here, multiple bonds. So a double carbon, let's see, where's the single carbon bond? Here it is. Single carbon bond is 347. So you get 2 bonds, 614. It's a stronger bond. 3 bonds, you get 838. Right? So that wasn't linear either. 347 to 614 is almost double, not quite. And then another bond, 3 plus 6 would be 900. It's not quite 900. Okay, so why do you need to know these values? Well, if you know the bond energies, you can calculate the delta H for any reaction. Right? Oh, flip too far. Oh, here we go. I've already said this before. That's not new. I already told you that before. It's in black and white here. Here we go. You can calculate the enthalpy of a reaction if you add up the bonds that were broken. What's the energy to break the bonds? And then subtract how much energy do you get back when the bonds reform. So these are all going to be positive values. These are all going to be positive values. We're using bond energies for both of them. So if you get more energy back when the bonds form than you had to put in to break them all, the overall is going to be negative, which means you get some energy out, and the reaction is exothermic. Right? So this sigma means sum of the terms. The N is moles, right? So that's the coefficient in your reaction. I'll show you an example in just a second. And this is the bond energy per mole of bonds. And they're always positive. Okay, so here's an example. We're going to take this compound, and notice that between here and here, the only thing we've done is put the carbon over here attached to this carbon rather than attached to the nitrogen. So it would be like this. And convention, the way that we write organic compounds like this, is when we write this, we actually mean this. Right? It's the carbon that's bound to the next atom. Like that. And then we have these bound to the carbon there. Now when we go to this one, we still have this group, but now it's bound to the carbon. Okay? So if we take the formula, the bonds that are broken, so which bonds are broken? The ones from the reactant. These bonds must be broken. So how many single carbon-hydrogen bonds do you have? You have 3 carbon-hydrogen bonds. You have 1 carbon-nitrogen bond. And you have 1 nitrogen-carbon bond. Those have to be broken. And then the ones that are formed on this side are 3 carbon-hydrogens. And 1 carbon-carbon. And 1 nitrogen-carbon. Okay? So this one is really easy. We've already taken the moles into account, like 3 of these, 1 of those, 1 of those. So we need to do this one and subtract that one. But look, if you take this one and subtract that one, what do you get? 0 difference. If you take this one and subtract that one, what do you get? 0 difference. So really, we only need to know this one. 1 carbon nitrogen minus 1 carbon carbon. 1 carbon nitrogen is 305, 1 carbon carbon is 347. What's the difference? This one's negative now. So that means the difference is 32? No, 42. Minus 42 kilojoules per mole. I mean, you can go ahead and go in and do the whole calculation, but why bother when you can simplify it? That difference is 0, this difference is 0. You only need to be concerned with those 2. Okay, now it's time to pause. I know I was rushing, but we're there. And we'll pick it up there on Wednesday and finish the discussion of general concepts of bonding. And what we're going to look at, it'd be good for you to read the text. Well, that's always the case. When you come to class, read the chapter first, rather than get it cold from me. Then we're going to learn how to draw Lewis dot structures and determine geometries of molecules. Okay, that's all I got for today, and we'll pick it up here on Wednesday. Let's see, did I miss anybody? 1, 2, 3, 4, 5. I think I got everybody that's attending covered. There. Yeah. Okay. So if nobody has any questions or comments, we'll call it a day. Stop the share.